Uh,
Yes, Dr. Saab. Today it is from 4 o'clock because Professor Rajan Singh is having some other commitment at 3 o'clock. So
ठीक है
today it is from 4 to 6.
ठीक है right.
So, Professor Rajan Singh, welcome. Can you hear me?
Yeah, hello.
Hello, welcome, Professor Rajan
Yeah,
Singh,
hello.
to our
Yes.
Sir,
AICT Academy.
a very good afternoon, sir.
Yeah,
Welcome,
very good
Sir
afternoon.
Rajendra Singh.
Thanks.
So I formally start the session. So all the participants, I again welcome you to this quantum QT-10 FDP, which is basically on solid state physics for quantum technologies. And it's a matter of great honor and pleasure for us to have Professor Rajendra Singh with us. Professor Rajendra Singh is the project director of QFD Foundation, Quantum Materials and QMD Foundation, Quantum Materials and Devices at IIT Delhi. As you know, Government of India has established 4 quantum T-hubs at different places of the country. And one of them is at IIT Delhi, and Professor Rajendra Singh is basically the project director for this T-hub, which is basically QMD Foundation, Quantum Materials and the Devices. And it's like, to have Professor Rajendra Singh with us is like biggest success for this FDP. The director of one of the T-hubs in the country is delivering lectures at our FDP. We consider it as the biggest success of our FDP, which is basically aligned with the QT-10 minor program of AICT in collaboration with DST. And it is basically one of the minor, which is QT-10, quantum solid state physics for quantum technology. So, participants, I welcome you all, and I'll briefly introduce Professor Rajan Singh here. Professor Rajan Singh is a professor in Department of Physics at IIT Delhi and also serves as the principal investigator of the Advanced Semiconductor Materials and Devices Group, along with being a joint faculty member at Department of Electrical Engineering at IIT Delhi. Professor Singh completed his master's in physics from Dehradun in 1995 and obtained his PhD from Jawaharlal Nehru University in 2001. During his PhD, he has focused on impact of swift heavy ion radiation on the electrical properties of semiconductors such as silicon and gallium arsenide. He further enriched his research experience through postdoctoral work at Walter Schottky Institute, Technical University of Munich, and the Max Planck Institute of Microstructure Physics, Germany, where he worked on advanced semiconductor device fabrication, wafer bonding, and layer engineering techniques. He joined IIT Delhi in November 2006 as a faculty in Department of Physics, and he has made significant contributions since then to the semiconductor research and nanotechnology at IIT Delhi. His research interests include gallium arsenide, gallium nitride, and gallium oxide-based devices, semiconductor nanowires, wafer bonding, 2D quantum materials, and advanced growth and nanofabrication techniques. Professor Rajan Singh has played a key role in establishing the Nanoscale Research Facility, NRF facility, which is a very well-known facility across the country at IIT Delhi. Professor Singh has published more than 200 research papers in International Journal of Repute, and Professor Singh has been recognized for his excellence in teaching and research with many prestigious awards, including MRSI Medal in 2017 and Teaching Excellence Award at IIT Delhi in 2018. So, sir, I again welcome you to our FDP. In this FDP, we have more than 750 participants who have registered for this FDP. It's a basically 40 hours FDP program in online mode, and the syllabus is aligned with the QT-10 of AICT minor program. And the credit which the candidates will earn, these credits are recognized for their degrees also. If we have the UG PG students are attending this course, so they can use those credits for their programs also. It is as per the guidelines of the Ministry of Information and Electronics and Information Technology and as per AICT. In this FDP, so I just give a brief to you. We are daily having 2 lectures, and then because it's a course, so the participants has to appear for the exam also. So we are conducting 3 quiz. Like second quiz recently in this last Sunday we completed, and then third quiz we will be having at the last of this FDP. And the best score out of these 3 quizzes will be taken as the final score. And on the basis of that, we will be giving the grades and the marks to all the participants. And then the certificates will be distributed. And sir, in this FDP, because we have a large number of participants, so participants are not allowed to use their microphone during the lecture. Obviously, they can write or they can drop the questions, whatever are coming in their minds during your talk. And at the last of the talk, let's say we are starting at 4, so around 4:50 or 4:55, in the last 5-10 minutes, we will take the questions, so that one by one, all those questions which have been written in the chat window, we can discuss with the participants. And here, sir, we have Professor Emmanuel Pilli also with us, who is a professor at MNIT Jaipur in Computer Science and Engineering Department. Professor Pilli is basically the main person who is looking after all these FDPs related to quantum technologies, which are aligned with the minor program of AICT. So Professor Pilli has taken all the pain to introduce these FDPs, which are basically the joint FDPs among all 7 EICT academies in the country. So with this, I would request Professor Pilli to please say a few words here. Yeah, Professor Pilli, over to you. Professor Pilli, your voice is not audible. Can you hear me? I think it seems some internet connection issues with him. Professor Pilli, Professor Emmanuel Pilli, can you hear me? He has logged in with some other system, I think.
Rahul sir?
Yes, we can hear you. Yeah, yes, please. I welcome you here, and I request you to say a few words for this, for our speaker and for our participants.
Right, sir. Thank you so much. Sorry for the inconvenience. Suddenly there was some issue with the internet. I had to log out and log in from another system. Welcome, Professor Rajendra Singh, and it was nice to meet you. Now we have had email exchanges, but thank you so much for joining. And it's a great privilege for us today that you are here as one of the director of the 4 vertical hubs. Participants, I have shared many times that National Quantum Mission has 4 hubs. One is quantum computing, one is quantum communication. The third one is quantum materials and devices, and the fourth one is quantum sensing. And we are privileged that one of the technical hubs director is with us today to share his thoughts about the National Quantum Mission, the vertical, and the challenges. And we thank Rahul Singhal sir also, who has coordinated and invited Professor Rajendra Singh to join. So without wasting much time, sir, I would like to just say that we have completed 9 courses, QT-001. That is where we started, and we have now completed QT-09. This is QT-10. So every lecture, every course had 40 lectures. So we have about 400 hours of quantum lectures recorded and fully available for any faculty member who is interested to view the lectures. Any student can view the lectures. And your lecture is going to be one of them now, being added into the 11th course, that is into the 10th course, that is QT-10, and we are very happy that you are here. So without taking much time, and then we just want to also acknowledge that in all the 10 courses, we have trained more than 10,000 faculty members certified Certified faculty members are around 10,000. So that's a great achievement. And every program has about 1,000 participants. Of course, this program also has about 900 plus participants. Many are joining and some of them have joined. So I thank you so much for sparing your time, and it's a privilege that somebody who has worked in the Max Planck Institute is with us today to talk about the quantum, which was based on much of the work done by Professor Max Planck. So over to you, sir, and over to Professor Rahul Singhal to take it forward. Thank you so much, sir.
Yeah, thank you, Professor Tilly. So may I now request Professor Rajen Singh to please start his lecture.
So can you see my?
Yes, sir, your screen is visible.
Maybe just you need to full screen. Yes, sir.
Yes. Your microphone is muted.
Now I am audible.
Yes, sir. You are audible.
Hello.
Yes, sir. We can hear you.
Okay. Now everything fine. So in between anything comes, maybe you can just send me WhatsApp so that, because sometimes I see there is to me. So right now it is everything fine. My are visible. It is, and I am audible.
Yes. Can you please go to your second slide?
Yes. Second slide.
I
It's
think
moving?
no, sir. It's still on fast. This slide. It's not moving. Now it's on second. Now it's moving.
No.
Yes. Now it's moving.
Okay.
Yes.
Okay. Maybe there is a gap actually. So now it is on second.
Yes. Now it is on second.
Okay. So I think what I will do is, let me just
Professor Rajen Singh, you are not audible actually. We can't hear you. No, still we can't hear you. हमारा ही on करो. Your video is visible, but audio is not coming. Audio is not coming. Mm, No, sir. Still, it is showing your microphone is muted. Yeah, you can leave the site. Mhm. You can log in and again. You can log out and log in again.
I think there is some internet issue there or something.
Yes, sir. It seems some internet issue at his end, so maybe he is again logging. I requested him to log out and again log in.
Yes.
Our proposal, I think, has been sent to him only, na? That our minor quantum proposal. Muted.
This has gone to QT. This has gone to that sensing because West
Oh,
region,
fine.
West region, they have sent to Bombay.
Bombay. Okay. I think today he's in Dehradun, so he's joining from there. So might be some issue at that Dehradun center.
Yeah,
The
maybe.
connectivity issue. He has joined again.
So can you hear me now?
Yes,
sir.
yes, sir. Much better.
Is it fine now?
Yes, it's fine. We can start now.
Okay. So yeah, so I just started with a like let's say discussion about this national quantum mission, and I think this is very important. Solid state physics for quantum technologies, and Professor Emmanuel has also talked about core hubs. So how, like let's say, my talk is structured is I'm first going to very briefly talk about IIT Delhi, just one slide what we are doing here, and then like let's say the national quantum mission, and after that I will switch over to the thematic hubs, and under the thematic hubs I will talk about the various mandates of each of these thematic hubs, and switching over to our, like let's say, thematic hub at IIT Delhi, which is on quantum materials and devices, and the future directions. So this will be first part of my talk, and in the second part, actually the second lecture, eventually, like let's say after a break, taking Q&A, I will go into the technical part of this quantum and material devices. So I think most of you know about IIT Delhi, but just to let's say give a very let's say concise form, the summary of what we are located in Hojkas, about 320 acres of land. But we also have two more satellite campuses. One is in Sonipat, which is about 50 acres, and we have a big central research facility and techno park, which is there. And we also have another campus at Abu Dhabi, which is IIT Delhi Abu Dhabi. And we have programs on material, not energy studies, and computer science and engineering right now there. It's not a full-fledged campus right now. And the number of students, we are about 12,000 students here in the campus, and about 3,600 are PhD students. So you can see that we are let's say no more only like undergrad, but it's let's say the PG students also, whose majority is there, and about 730 faculties. And last year, let's say 2026 and 2025, this QS ranking has been let's say consistently number 1 in India, but globally 123. It's also a matter of pride for us. So this is just about the institution where I come from. But now directly I will jump to the National Quantum Mission. So I think many of you have heard about. I will take some of your queries later on. So let me just finish this part, and then whatever queries you have within this stipulated time, whatever we can cover, I will try to answer them. So a few years back, actually, this quantum technologies related discussion in India, it's going on since let's say, as far as I remember, since last 5 or 6 years. It's not let's say it just got announced 2 years back only, but there was a lot of homework that we people were doing since last 5-6 years. And this is the culmination, that is the announcement of National Quantum Mission in 2023. And what has been realized is that overall the quantum technologies are going to define a lot of things in the coming time. One thing is let's say the artificial intelligence, and second thing is the quantum technologies, which is going to define how many of our let's say various sectors, as you can see, uh,
Sir, your voice is not coming.
let's say no, China, USA, many countries in Europe, and Japan, all these countries are having their own let's say quantum initiatives or quantum missions. And within the same kind of let's say
Sir, sorry to disturb.
tradition.
Sorry to disturb you. Your
Yes.
screen is not presented. Can you share it again?
Your screen is not.
Screen is not visible?
Yes, sir.
No, sir. The sharing has gone.
Sharing has gone.
Yes, sir. I can see only.
Now?
No.
Is it okay?
No, sir. No, it's still not visible. It's still not visible.
So why it is happening? Because I just share in the beginning, so it shall not.
Actually, now it is coming. Yeah, actually, your initially your audio was not coming, and then after a few seconds of that, screen sharing was also lost. Now it is coming. Now it's okay.
Okay, so this is on the third, let's say this National Quantum Mission slide. Are you seeing the National Quantum Mission slide?
Yes, yes, sir. We can see it.
Yes, sir, we can see it.
Okay. Just let's say, tell me in between if there is any issue.
Okay.
So this is let's say what I was talking about, the quantum technologies, how they are applicable to various sectors, and it is let's say very, very critical, and that's why this mission has been announced. So this was announced in April 2023, almost let's say as such 3 years back. looks that it was announced 3 years back, but the activities more or less have started only in the last 1 year. And this is like, let's say, huge, almost like, let's say, 700 million USD, about 6,000 CR will be invested in the, like, let's say, coming years up to 2031. So the duration of this national quantum mission is up to 2031. We are already in 2026, and under this national quantum mission, the activities, that research and technology activities or research and innovation in the quantum tech area have been divided under 4 hubs. Okay. So one of the hubs is at IIC Bangalore, which is like, let's say, what we call the T hub or thematic hub, which is on quantum computing. Okay. And this framework is working on hub, spoke, and spike model. Okay. So there is a central institution, what we call the hub, like IIC Bangalore in this case for quantum computing. And then there are, like, let us say, Raman Research Institution, which is a spoke, which is working on a particular technology platform. And with this institution, there are many spikes associated, which are helping Raman Research Institute, which is a lead institute, helping in developing that platform. Okay, what it is, I will come to that when I am going to discuss about our own quantum materials and devices, spoke and spike. So you can see it is like, let's say, hub, spoke, and spike. So many institutions are involved in this complete endeavor and effort. Second one is quantum communication, which is at IIT Madras jointly with CDAC. And here also it is like many institutions which are involved, again in hub, spoke, and spike model. The third one on quantum sensing and metrology is at IIT Bombay. And the fourth one, which is at IIT Delhi, it is on quantum materials and devices. Okay. So here also you can see there are, like, let's say, 3 spokes and many other spikes. So it is a hub, spoke, and spike. So hub, let's say, but we have 4 hubs are there: IC Bangalore, IIT Madras, Bombay, and Delhi. So what are the key technology domains? Okay, what are the, I was talking about the technologies. What are the technologies that these hubs are supposed to develop? Okay, ultimately these are some research institutions, some educational institutions, some governments are who are going to develop these technologies. And finally, these technologies will be deployed in various sectors, as I was discussing: finance, defense, space, and automotive, and so on. I start with quantum technology. In the quantum technology, what you see is there are various platforms. See, as in classical computers, we use bits, actually, what we call classical bits. Their values are 0 and 1. Okay, so this 0 and 1 in classical computer is achieved by on and off state of a transistor, what we call the CMOS chip, okay, CMOS transistor. But for quantum computing, we use qubits. Okay, they are quantum bits, and they can exist in superposition of states between 0 and 1. So then infinite number of states are possible. But how to provide this 0 and 1? Okay, so it has to be a quantum state, 0 and 1. So these are provided by various materials and other, like, let's say, atomic level platforms. So this is what we call the superconducting qubit platform. Is on superconducting. Then there are qubits which are based upon the trapped ion. And similarly, photonic qubits are also there, neutral atom qubits are there, qubits based upon the semiconductor spins in semiconductor, like, let's say, transistors are there. There are talks of so computing platforms will be looked into. Okay, they will be, people are doing research on them, and later on it will be seen after a few years which of the platform is performing better. Okay, which is taking us to higher number of qubits, because there is a question how many qubits you can provide. So into higher number of qubits, whatever platform, like, let's say, provides it, ultimately we will be going for that one. Now come to the quantum communication, where key ideas are, like, let us say, what have been mentioned here: quantum cryptography and communication, free space quantum communication, and post quantum cryptography. These are the major technology themes of the quantum communication hub. And quantum sensing and metrology, we are going to develop very, very high, like let's say, sensitivity devices and sensors. So like atomic magnetometers, atomic clocks, and quantum radars, quantum gravimeters, and inertial and NV sensor based sensors. So the quantum sensing and metrology is actually, like let's say, looking only into the quantum sensor part, and whatever is required. You see, all these hubs are more or less like let's say have enough resources to develop any of these technologies, and there is a kind of flexibility also. Uh, how many resources shall be going to one particular technology domain or technology topic? So after that, there is a final one on quantum materials and devices, where, like let's say, at IIT Delhi, it is there, and it is actually, just a moment, 1 minute. Okay, sorry for the break. So what we are doing here is actually we are supposed to provide the materials as well as
Sir, you,
devices and component
yeah,
resources,
excuse me, sir.
which will be feeding into all the.
Yeah, sir,
Yes,
if possible, you
yes,
can turn your camera off so that all the signals will be going for audio.
yeah, yeah. Okay. Is it okay?
Yes, yes. Now voice is much better. Earlier it was intermittent. Now it is much better. Yes, sir.
Okay, so okay. So in this quantum materials and devices hub, what I was telling, that we are working jointly with all the three hubs to provide them the material as well as the devices and also the components, whatever is required. Let us say a superconducting thin film is required for the development of a superconducting qubit. So our hub actually, like let's say, can start developing those kind of materials. So our work is only limited up to the material development and device development. We are not going to develop the quantum computer. Quantum computer will be developed by the quantum computing hub. That is their responsibility. Our responsibility will be, suppose they ask for a particular material, they ask for a particular device, and that is what, like let's say, we are going to develop. So this is actually the way how four hubs have been, like let's say, organized. So here one important thing is very, very important, which I would like to emphasize to all the participants, that this national quantum mission is based upon the deliverables. Okay, what are the deliverables we are going to provide? So it is not only, like let's say, blue sky research or open ended research where we are looking primarily into high impact factor publication. It is also, like let's say, promoted, but more emphasis is on the deliverables. So for example, in the quantum computing, one of the key deliverables is developing intermediate scale quantum computers with 50 to 1000 physical qubits. Okay, so right now at the national level, we have developed technology based upon superconducting and photonic qubits, where we can go up to the 6 physical qubit. You see, this what we have done in India right now. We are not talking about what is done outside or what we are procuring from outside. We have developed 6 qubit. We want to, over the years, in the coming years, we want to go to 50 or 100, eventually to 500 physical qubits. So this is a very clear set goal. There shall not be any deviation from there. Okay, we shall not be talking about only research publication. It shall be the number of qubits which, like let's say, can be manufactured, which can also be developed. Second thing in the quantum communication is very clear cut deliverable: develop secure quantum communication across 2000 kilometer. Okay, it's very specific, 2000 kilometer within India. So it has to be, it can be fiber based, it can be satellite based, and develop multi-node quantum networks. This is what is required for development of quantum communication over such large scale of 2000 kilometer, which, like let's say, some years back, China already reported satellite based communication using their MIQS satellite. Under the quantum sensing and metrology, there is a development of magnetometer. But magnetometer with a particular value of sensitivity, which is, let us say in this case, is about 1 femtotesla per square hertz. Then development of gravimeters of very high sensitivity, or development of atomic clocks with 10 to the power minus 19 fractional instability. So this is like, let's say, going into the extreme of the technology. That is what I mean to say. And under the quantum materials and devices hub, I'm going to tell more about it. So like, let's say, I won't elaborate it here, because ultimately, like, let's say, I will be discussing more about the quantum materials and devices hub activities. So under the quantum computing, as you can see, this is what, like, let's say, a little bit more elaboration, that there are so many institutions which are serving as, like, let us say, the spoke. So there is one on Raman Research Institute, which is developing, like, let's say, the technology platform for quantum qubits based on photons. At IIT Delhi and IIT Bombay, they are developing qubits based upon the semiconductor spins. Okay, semiconductor spin based qubit will be developed. So this is a specific activity, and going to, let us say, 50 qubits. Then there is at Tata Institute of Fundamental Research, which are going to develop the technology for fabrication and demonstration of a quantum computer based upon superconducting qubits. So it is a quantum computer, but based upon superconducting qubits, and going up to maximum, or like, let's say, eventually we will be going up to 500 or eventually 1000 qubits. And then at IC Bangalore, photonic qubits will be the activity, and there will be, like, at Raman Research Institute, it is based upon the neutral atom neutral atom qubits will be there. So all these, like, let's say, technology platforms which are used for the qubit formation, qubit fabrication, will be, like, explored and developed. It's not only pure exploration, but it is the development of the technology also. Eventually you will see that one of these technologies will win. It will be faster development in one of these technologies, will be based upon that technology. So goals are very much clear here. In the quantum communication, you can see that so many institutions, including ISRO, is also there. ISRO is developing quantum communication for satellite based like technology, and they are having their own satellites, and they have done some proof of concept demonstration they are trying to show. CDOT is also involved, and then IIT Delhi is involved in fiber based, like, let's say, quantum communication. Raman Research Institute is also there, and similarly IIT Madras is also involved in setting up, like, let's say, these networks. So right now all these fiber optic cables they are exploring, which can go up to, like, let's say, connecting Chennai to, let us say, Bangalore or other cities. They are laying down the foundations of this fiber optic network and testing their systems. So some very small proof of concept, like, let's say, demonstration of quantum communications have already been done also over 200 kilometer, but eventually we will go up to the 2000 kilometer. Then finally, like, let's say, the third one is the quantum technology. As I have told you, that they are going to develop NV diamond. So there is a CVD diamond, what we call the lab grown diamond. So on lab grown diamond, there will are specific defect centers, what we call nitrogen vacancy centers. So these nitrogen vacancy centers will be utilized for the development of various, like, let's say, devices, something like magnetometer, highly sensitive magnetometers, and they will be used for certain applications like mapping of minerals under the, like, let's say, earth in India. All these applications will be coming up in future, and also the NV diamond based microscope. So finally, this is like, let's say, the hub at IIT Delhi, and I will elaborate now. I will start elaborating little bit more, and then what I will do is I will go into the general theme of all these four hubs. What we are doing apart from technology, it's not only technology. What else we are doing? So here, as I told you, our aim is, our objective is to supply with the material and device and components to the other three hubs. So what we are doing is, it is being done by the three, like, let's say, technology groups. Spokes are called technology groups. Okay, there is a hub and there is a technology group which is a spoke. So one of the spokes is at IIT Delhi, and the spikes are at various IITs and defense. So this is based upon 3-5 semiconductor based quantum devices. So in my second lecture, I will elaborate this part more. So we can wait till then. Second one is at IIT Bombay, which is on 2D quantum materials and devices. Okay, what devices we are making, what kind of, like, let's say, materials we are exploring and developing, this also I will tell. And the third one is at IIT Kharagpur, which is developing silicon nitride thin film based integrated quantum photonics, and they are also developing various materials as well as device technologies. So this is what we have: three technology groups, what we call the TGs: Delhi, Bombay and Kharagpur. So if you see, overall, this is like, let's say, the mapping of institutions under four thematic hubs. So there are four hubs, but then there are 14 technology groups or technical groups. Okay. In each of these technical groups, there are many institutions. There could be 5 institutions, there could be 6 or even more also. So overall, what has, like, let's say, it has led to, there are about 152 researchers, primarily the faculty from 43 institutions, which are involved as a lead or member. Lead, the leader of the technology group, and member is a kind of spike coming from a spike institution involved in the four technology hubs. So you can read, actually, I will not go through all these list of institution. There are a lot of IITs are involved, ICERs are there, and SSPL, a defense lab, CDOT is also there, and ISRO is also involved in this activity. So you can see right now there is a very good amount of distribution among various institutions in India, and in future definitely this kind of number of institutions shall increase with the, like, let's say, as the National Quantum Mission will proceed further. So this is a very, very important slide, and here, like, let's say, it connects to various activities of the hubs with the technology development. So I'm just taking quantum materials and devices as, like, example, but similar kind of activities are being done by the other three hubs also. So one of the key aims, as I have said, is the development of research uh, and innovation ecosystem in India in the area of quantum technology. So how it will be done? It will be done by the development of appropriate and suitable technologies. So these technologies will be, like, let's say, developed, and they will also be given by our departments and line ministries. So time to time we are being approached by space, we are being approached by Department of Atomic Energy and also the defense, that these are the problems that they would like to, like, let's say, tackle, and how, like, let's say, this can be tackled. So then we start making a group and explore various institutions, their capabilities, and how it can be done. Currently, as I have shown you, 14 technical groups are already there, but in future there may be a few more technology groups which might be coming, or maybe a few spike groups will be coming. So the technology development as per the requirement. Technology development not just for the sake of technology development. It shall be guided by some department or line ministry. It shall be a requirement of a government of India, some institutions, some private, like, let's say, industry. We are not going to do anything independently if it is not a requirement. Okay, so this is a very, very important thing which you shall, like, let's say, as a message you can keep with yourself. Second thing is the startup and industry partnership. So at the outset we are supporting, like, let's say, along with the technology groups. I am not going much about the startups, but we have dedicated funds. So you see, these four mandates what I am talking about right now, we have dedicated funds for that one. So for technology development we have certain amount of funds, for startups we have certain amount of funds, and we cannot, like, let's say, exchange between them. Startup fund can be utilized only for the startup. Okay, and another one is, which today I'm giving a talk in front of, like, let's say, all of you, which is a part of our human resource development or skill development in quantum technology. If we want to develop a technology at the, like, let's say, massive scale, we need to have skillful people also, people who have, like, let's say, knowledge in that area. So knowledge creation, like, let's say, is an important part. Okay, with the knowledge creation only the innovation will come later on. So we have to enhance the core research base in India. So this is what is a very important mandate. and we are doing some activities within this framework, and I will tell you about that. But whatever FDP, like this faculty development program, MNIT Jaipur and partners are doing, this is also along the same direction. Okay. So national and international collaborations, not to mention too much, like let's say, we are open to, like let's say, collaborations with the international partnerships. We are also developing, including exchange students, joint development of technologies. Right now the problem is that nobody wants to share the quantum technology they are developing, because it is a very, very, like let's say, strategic sector. But if there are some friendly countries, they want to jointly develop certain technologies with us, we are having funds for that also. This is actually, like let's say, the mandate. I have told you, technology human resource and international lab. All the are, like let us say, doing the same, but then they are doing in their domain. Quantum computing is doing in quantum computing domain. Communication hub is doing in their domain. We are doing in the domain of quantum materials and devices. So if you see the startup engagement, because it's very important to tell about this one, because a lot of our enthusiastic undergrads and even, like let's say, PhD students, they might be keen to have a startup in the area of quantum technology. So we have good opportunities for them. So what happens is, we are, like let's say, promoting the startup ecosystem in India. Okay, but startups have to come up with an idea where the deliverable that they have, the technology that they are developing, is in line with what the quantum mission wants. Okay, again, it's the same thing. Suppose they are going to develop a technology which is based upon superconducting qubit, or it can help superconducting qubit technology development. So what will happen is, then it can be supported. If it is a material related thing, we can support that. Okay, so, and we will also facilitate the technology transition. If the startup after a few years is mature to transfer the technology, and that also can be facilitated. We have the resources, we have the connects, so we can provide all the available resources available with us to you also, and our connects also. And each of these hubs are also going to create big facilities, national facilities. I'm going to talk about one of those facilities which we are developing at IIT Delhi, and this will also be available to the startups. You see, we are developing a complete quantum ecosystem in India, and all the institutions are a partner in that one. They are stakeholders. This facility, national facility which we are going to create, it doesn't only belong to IIT Delhi. It belongs to the whole quantum community. On some sharing basis, payment basis, this can be, like let us say, utilized by anyone who has a good idea in the quantum area, but provided they have certain funds from the quantum mission. Okay, so now come to the second thing, is the quantum awareness program. So you see, we, as I told you, we want to have a capacity build up, okay, through workshops, through training programs. So this is a kind of online workshop, but we are also organizing, like let's say, offline workshops, because then you can interact directly with the faculty. We can showcase you also what are the technologies which are being developed, and you can directly interact with the researchers, PhD students, and so on. So then the hands-on programs, and then the educational initiatives, I will talk about that also briefly. And enhance awareness. So in the awareness, this is, like let's say, today's one of the lecture that I am giving you, it is one step in that direction. Okay, this is, like let's say, enhancing the awareness. After the I finish my lecture, definitely you will be knowing little bit more about the quantum mission and what we are doing actually, and how it has been structured. And also for the development of policies, okay, policy development in the quantum area. So in the capacity building, I think it has been mentioned also during the introduction part. So AICTE has developed a curriculum on technologies. Okay, I think many of you may be aware of it, and if you are not aware, you can go into the AICTE website and download the curriculum and the syllabus. So BTech minor in quantum technology, and there is a full-fledged MTech in quantum technology. So these two programs have been developed, and they were launched on 24th December 2024 and 28th August 2025. So there is a complete syllabus is there. Okay, and right now this course has been already going to be adopted by a few engineering institutions. More are in the pipeline, and quantum curriculum will be developed. Video lecture series for student learning will also be developed, and faculty development programs. So the kind of program you are doing, it is also, like, let's say, along the same direction. And another important thing is the curriculum development, that within this curriculum development, AICT and National Quantum Mission has come up with a plan to establish almost, like, let's say, about 100 quantum teaching labs across various engineering institutions, engineering, or, like, let's say, the universities. So 100 quantum teaching labs will be established, and each of these teaching lab will be provided with some fund from the National Quantum Mission. So currently there was an open call. I remember some 7-8 months back, or even more than that, and 400 proposals were received. Out of that 423 quantum teaching lab proposals have been accepted, and now the sanction letter has gone to them, and these will be funded through the quantum hubs. So what has happened is, some of the institutions which are in the northern part of India, they will be, like, let's say, mentored and supported by quantum hub at IIT Delhi, like UP, Punjab, Delhi, Haryana, and so many, like, let's say, states. But some of the states in middle part of India, or southern India, or eastern India, they will be, like, let's say, looked after by the other three hubs. Okay, so there is a kind of division actually among these four hubs. So all, like, let's say, the northern Indian states, starting from UP and upwards, they are with the quantum hub, which is, like, let's say, QMD hub at IIT Delhi. And there are more proposals which have come up, and right now we are looking into them. So this is, like, let's say, to those faculty who are in certain engineering institutions, you can also apprise your admin and your faculty about this opportunity, that there proposal, and then, like, let's say, with due evaluation, the whole process completed. If you are successful, then there are certain funds which will be provided to you, where you can set up the quantum teaching lab. And in this curriculum we have developed, all these like, let's say, experiments which you can incorporate in it are also given. You can also incorporate new quantum experiments, but some kind of, like, let's say, list of these experiments is already given. So apart from that one, there were two dedicated calls for the quantum algorithm development, application oriented development. So this is in addition to this one. So quantum algorithms, so those people who are, like, let's say, from specifically computer science background or electronics background, they can also explore this possibility of quantum algorithm. But this particular, like, let's say, activity is completely with the quantum computing hub at IC Bangalore, because we are purely materials and devices hub. So for anything you want to know about quantum algorithm, you can go into the IC Bangalore hub. Important thing I would like to tell you is that all the four hubs have a dedicated, like, let's say, team, and this is each one of them is a Section 8 company, and we have a CEO, CTO, and a complete team, including technology managers. And we have a website, there are numbers, there are emails. So you don't need to send mail to my IIT Delhi email, because that's already crowded. Your email you can send to the CEO, or there's a, like, let's say, QMD hub at the rate, so some kind of email is there. I will show you at the end. You can go to our website, all the details are there. So you just contact the person there, and they will reply to you. Okay, so this is about, like, let's say. And as I was telling you, events by QMD Foundation, we are doing faculty development program also. We are doing workshops on quantum technologies, seminars with the industry, like this one was done with the Horiba, and hands-on workshop on quantum photonics and RF tools. This was done with the Keysight Technologies. And governing board is Mr. Ajay Chaudhary, who is the co-founder of HCL Technology. So he is our mission governing board chairperson, and he also, like, let's say, visits us and gives us the advice and how to take, like, let's say, further these technologies. And we gain a lot from his advice and support. And like, let's say, DST secretary MOU signing with our hub and so on. So various activities are going on and various events are going on with the Quantum QMD Foundation. So what now, like, let's say, I will, as I was telling you, that we have this QMD Foundation. This is a Section 8 company and this is the team at IIT Delhi for QMD Foundation, Professor Samresh Das. He is also, like, let's say, a very key player in our hub. Myself, I am the project director. Our C back, and he is, like, let's say, overall, he is looking after every activity of the QMD Foundation. And then you can see, like, let's say, we have technology managers, Dr. Nayak, Tejas Nayak, Dr. Nahid Chaudhary, technology manager. Then we have accounts people, project assistant. So these are the people who will help you out in clearing any of your doubts. So contact will be this Quantum Foundation IITD. And this is the web page. Okay, https. You just go there. A lot of information is already there. Okay, whatever I am telling, there are a lot of information already there. And still, if you have doubt, you can just email here. There might be some number also. You can reach out there, or whenever you are visiting IIT Delhi, you can go, like, let's say, you can contact Mr. Aditya Vyas or Dr. Shiv Kumar, and you can go and meet with them also. We have a separate office in the Research and Innovation Park. It is inside the same main campus, and you can meet with them also with some prior appointment. So I think this was, like, let's say, overall the structure of the QMD Foundation. And I think I would like to take queries from the participants because they might be having a lot of doubts. So before going into the technology development part, so I will try to take a break and take the questions and answers. So thank you. So it's over to you, Professor
Yes,
Rahul.
thank you. Thank you, Professor Rajendra Singh, for
I can start taking another 10 minutes.
yes. Yes. Thank you, Professor Rajendra Singh, for a very, very informative session. You have covered all four thematic hubs across the country, and you have very beautifully explained the National Quantum Mission objectives, their mandates, and their working procedures and other things. Just to add to your lecture for your just knowledge, I would like to bring it to your knowledge that at MNIT Jaipur, we have also applied for one quantum teaching lab, and the proposal which was there last year, we
Yes.
applied also, and that our proposal is also under evaluation mode. I think it has been sent to IIT Bombay T Hub, and we wanted to develop one teaching quantum lab at our end. We are proposing one quantum minor program also for our BTech students at
Okay, good.
yes, at MNIT Jaipur, being a NIT of state of Rajasthan, we are having almost 4 to 5,000 BTech students, as well as another 2,000 or 2,500 MTech and PhD students. So we would be looking forward to have more collaboration with the National Quantum Mission through the four thematic hubs, so that at least one of the institute will also, especially in the state of Rajasthan, because the map of India which you showed, I was looking very carefully, but unfortunately I couldn't see any institute from the state of Rajasthan which is directly connected with any of the T hubs. So MNIT Jaipur will try to, take a lead from the state of Rajasthan in this area. As my director was, Professor N.P. Patil was also looking to join today, but due to some other appointment with some other meeting with the ministry people, at the same time he could not join. Although I requested him, and he was very keen or curious to attend this lecture. So Professor Patil will also be joining at some other time with us in this FDP. So thank you, sir. Thank you very much for a very, very nice and very, very informative session. And I'm sure that all the participants, because since day one, we started this FDP on 8th of May, And then since day one, many participants were asking the questions about these thematic hubs, their roles, how can they connect with it, how can they be benefited by taking some training, some courses through this thematic sub of NQM, National Quantum Missions. So thank you very much, sir. Now we can take a few questions
Yeah,
and
so
then
Professor Rahul,
yes,
yeah,
sir.
so before we start taking the Q&A session, so our CEO, Mr. Aditya Vyas, he himself is from Jaipur, so he is also online. So maybe
Okay.
a few words he can also let's say tell to the participants. And he joined us 4 months back. And I would
Okay.
like Mr. Aditya to introduce himself, and maybe if possible he can just open his video also, and then introduce himself to the participants. And let's say he is the key contact point at the QMD Foundation. So Mr. Aditya, are you here?
Yes, it will be too nice to have Dr. Aditya with us. And
I'm just trying to ask him.
yes, sir. Yes, sir.
He just told me that I asked him also to be present.
Okay, he's asking to, we are giving an option to unmute because he is joining through a participant.
Yeah, Mr. Aditya Vyas. You can just see his
Yeah,
name, Mr. Aditya
yeah,
Vyas.
yes. We are giving the
Yeah,
option to
so that he can open his video also. Okay.
ADIT.
Yeah, Mr. Aditya Vyas, just see the name.
Yes, sir. Give me a moment.
Yeah.
Yes. Foundation.
Yeah, it is there. Aditya QMD Foundation.
Yes, Mr.
So yeah,
Aditya, now
Aditya
you
is
can.
here finally.
Yeah.
Your own Jaipur guy.
I just
That's
heard my
great.
intro. He's from Jaipur, so I think
Yes,
that
Aditya,
added some
you
interest
you
for
are from
MNIT.
you are from Jaipur, like so you are like a family member to us.
Thank you so much, sir. A very good evening, everyone. Thank you, Singh sir, and thank you, EICT team, MNIT Jaipur. I think sir has introduced QMD Foundation and NQM. I was attending for the past 40 odd minutes, sir's talk. So all those who are working in the area of quantum, specifically materials and devices, we would love to see how we can support you. As sir mentioned, there are a few ways in which the National Quantum Mission can be of support. The easiest way at this point of time is for people who are building their own startup in this direction. So if the initial research from TRL level 1 to 3, that is from your idea till proof of concept, has been done in the labs of MNIT and other esteemed institutes, I think that is the right time to reach out to QMD, get into the startup mode, and start building your journey towards building an enterprise into this upcoming area. I also saw some questions, Singh sir, which are related to research and research support. I think the lab support, etc., would be available as and when specific facilities which might be required for the students and researchers is set up and is available apart from what the researchers need for their core research at our end. But I'm not very sure if funding support would be available for research, because the next call for applications might take some time, and it is usually regulated by DST. So it takes much longer than a usual call for applications do. But I think startup is the easiest way. And if there is anything else that we can be of support, please do reach out to us. I'll just put in email address in the chat box for all of you, wherein you can reach out to us, and we'll be happy to respond to you from time to time as might be required from you. Not able to find the, okay, I think chat is right now disabled for me. Okay, I can see it now. So this is my email address. You can reach out to me on this. Sir, back to you.
Okay. So thanks, Aditya, for your let's say kind introduction. And then maybe Professor Rahul, we can start taking up a few questions, because Aditya is also here. Some of the questions I think I can let's say transfer to him also. So let us have a couple of questions which are let's say
Yes,
more of
yes, Professor.
immediate importance.
Yes, Professor Rajan Singh, we can take the questions one by one. And thank you, Aditya, for being with us in our FDP. And
Thank you,
obviously,
sir.
like you have already written your email ID, I'm sure the participants who were very keen to have some relation with the National Quantum Mission, or to know about the methods or the procedures, how can they be connected or how can they utilize the facilities there, they would be writing to you on your email ID. So
Sure.
thank you, Aditya, and I invite you whenever you are coming to Jaipur, please visit our institute, MNIT Jaipur, so that in
Sure.
future we can have the good bonding between the two T-Hub at IIT Delhi and MNIT Jaipur.
Sure, sir.
Thank
I'm
you.
associated with certain faculties, sir, but I'll reach out to you next time I'm there.
Okay, that's
Thank you.
great. So Ankita, we can take questions one by one.
Yeah, just a few questions, 5-6 questions we can take up
Yes.
with some diversity.
Yes.
Sir, the first question is from Vinod Kumar. I want to open UG and PG courses, major in physics and minor in quantum computing. Requires a quantum computing lab. I want to establish it in my
So it got
university.
frozen.
Uh, kindly suggest me from where I can get to fund to establish it. Where, what is the process and where should I apply proposal for fund?
Professor Rajan Singh, can you hear?
Professor Singh, are you there? Perhaps I'll reply till sir joins back.
Yes, Aditya, you can reply.
Okay.
Yeah, you can.
So for UG and PG lab setup, DST had floated a call for applications. Professor Singh, can you hear us?
Yeah, now I can hear you. In between, I think all of you got frozen, so I could not hear you. I
Okay.
could not see
Okay.
you as such. So maybe, yeah, I could not listen to that question, but maybe Aditya, you can answer that.
Sure. So, sir, basically the query is that somebody wants to start UG and PG program in physics and in
Okay.
quantum computing at their institute, and they're looking to support from NQM, from QMD regarding the quantum computing lab and the funding support for the same. So I was just informing that DST NQM had called for proposals specifically for setting up of UG labs
Yes.
in specific institute.
Yes.
Currently, all the proposals which were received by DST are under consideration. 23 labs have been announced in the month of April, and approximately 77 more will be announced in the next round, which will take the number to 100 labs across India. So far, DST is not calling for new round of applications, but at the same time, the entire nation has been distributed among the 4 hubs. For example, we at QMD take care of North India, from JK to Uttar Pradesh and Uttarakhand. Rajasthan, for that matter, comes under the IIT Bombay hub, which is in sensing and metrology. Uh, so we all work together, but yeah, just for sake of convenience, it is divided across the 4 hubs. My request is that if it's a private university and if you have the funds available, you can design your own lab, and NQM and the hubs will be happy to support you in choosing the right facilities and setting up the model lab at your end. And also in promoting that lab. If it's a government university and there is funds available, I think you can pick up the same route. In case of paucity of funds, please wait for the next round or next call for applications for the setting up of quantum labs under NQM. It will come hopefully by the end of this year or next year, because right now this process will take up at least next 2 quarters. Back
Okay.
to you, Professor.
Thank you, sir.
Yeah.
Thank you, sir. Sir, the second question is, I intend to prepare a project proposal on quantum dots in the context of biology. For this, I require technical expertise and laboratory support. I kindly request your guidance and suggestions for potential collaborators.
So you see, at IIT Delhi, we are doing some work on, like, let's say, there is one Professor Shantanu Manna. He is leading this activity on quantum dots for single photon emitter. But that application, like, let's say, to biology, right now we don't from the biology background. And what can be done is the person who is asking this question, they can send this query to our, like, let's say, maybe the CEO or QMD, and then we can see, like, let's say, who could be the people who are working in biology, and then we can set up a meeting or some kind of discussion with the faculty. Okay.
Sir, the next question is, could you please share some insight how to start quantum related algorithm? Means, do we need to start learning about quantum technology or directly we can from somewhere else?
As such, like, let's say, you see, as our hub's expertise is not in the quantum algorithm, we can, like, let's say, like, divert your question to the quantum computing hub. But you see, quantum algorithm, as we can see, most of the people who are working in this area are from somewhere related to computer science and engineering or having some electronics background, and definitely you need to understand some basics of quantum computing, and need to have understanding of software, hardware, and all those things. And you can then, like, let's say, start proposing for a quantum algorithm. So IBM has actually a kind of, like, let's say, platform what we call Qiskit. You can go to the IBM platform, IBM website. So this Qiskit is there. You can learn that and start developing the quantum algorithm. But this is just, like, let's say, from a kind of non-expert view, but you can take a more expert view also by contacting the quantum computing hub at IC Bangalore.
So the next question is, I have been working as associate professor in physics. We are providing quantum technology minors. Can I apply for quantum teaching lab from National Quantum Missions?
Yeah, sure. You can apply for that one. There is already a call was there recently. More calls will be coming in the future. The faculty can apply for that one. There are certain conditions to be fulfilled. And once you have, like, let's say, the tick mark on all the check boxes, you can submit a proposal. And it will be evaluated by your corresponding, wherever, whichever state you are coming from. The hub who is looking after that state, your application or proposal will go to that particular.
Okay, thank you, sir. Sir, the next question is, to what extent can classical machine learning models predict the decoherence patterns of specific NQM-backed conducting qubits, and how can this data be integrated into a real-time circuit
So
weighting algorithm?
yeah. So again, as I'm telling that we, our hub is not having, like, let's say, that kind of necessary expertise to, like, let's say, correctly answer this question. Maybe you can forward it to us, and we can then, like, let's say, ask to the quantum computing hub to give a suitable reply to you. Okay, just write a message to us.
Okay, sure, sir. Thank you. There's another question. Under the National Quantum Mission, India is prioritizing specific material classes like superconductors, novel 5 semiconductor structures, and 2D topological materials for building qubits and single photon sources. Could you
Yes.
briefly outline the strategic roadmap for sourcing and synthesizing these materials locally?
Yeah. So
And
this.
what?
Yeah. So this is, like, let's say, the topic of my next talk. I'm going to talk about that, what we are doing currently, and what is the future perspective. I'm going to talk about that. And what are the
Okay.
resources required, what we are going to build up, how they will be synthesized. I will talk about that more in detail.
Okay, sir, the last question is, if an institution wishes to buy quantum lab devices directly within their own funding without waiting for DST approval of funding, how can they proceed? This is the last question.
Okay. So if an institution wants to buy, they are free to do that. Then they don't have to, if they have the funding available from their own resources, and if they need actually, like, let's say, some mentorship or some guidance from our hub, then we will be more than happy to provide that. We can actually, like, let's say, make a special arrangement also, so that, like, let's say, whatever some teaching lab experiments we are setting up here, you can take, like, let's say, some hint from that one, and set up the corresponding experiments in your own lab. So I think it's already a good thing that if you have your own resources and you want to start up a quantum teaching lab.
Okay, thank you, sir. The remaining questions we will be taking after the second lecture. And
Yeah.
sir, would you like to take a 5-minute break, or you would like to continue the second lecture?
Yeah, maybe just like let's say a few minutes of break. Then after 5 minutes, we will assemble again. Okay, for my next lecture. I'll
Okay,
just have
thank you
some.
so much, sir.
Yeah, yeah. I will again come
Thank
back.
you.
Yeah, thanks,
Thank you.
Aditya. Thanks.
Thank you so much. Dr. Santoshi. Dr. Santoshi, I think I can answer a question if you are there.
Yeah, go ahead.
Basically,
Aditya, go
yeah.
ahead.
So as I mentioned, based on geographical location, each proposal that has been sent for UG lab has been given to a certain hub, one of the 4 hubs for the initial shortlisting. For example, we have got North India. Similarly, ISC has got certain state proposals. So that is why your proposal is with the ISC, and they'll do the initial shortlisting, forward their recommendations to DST, and then DST will take the final call. I think that's all. Thank you so much, everyone. Bye-bye.
I again welcome you all to the second lecture of this FPP QT-10 Solid State Physics for Quantum Technology. Now I request Professor Rajendra Singh to continue his second lecture. Sir, are you able to?
Hello, can
Yes,
Yes, sir.
we can hear you. We can start the second lecture. Your voice is not coming, sir, now.
Sir, your voice is not coming.
Candidates, we are starting the second lecture. So Professor Rajan Singh will be joining. There was some issue of the connectivity. So he is just logging out and again he will join.
hello? Hello.
Yes, yes,
You
sir.
can
Yes,
you
sir.
can hear me, no?
Yes,
Okay.
yes, sir. We
I
can
will
hear you
just
now.
share. I will not share my video because that's going to take the bandwidth. So is it
Yes, sir.
visible?
Yes, sir. Your screen is visible.
Okay. Okay. So let me start with the second part, which is more technical. So as like let's say now you came to know about the structure of the National Quantum Mission and what are like let us say the four hubs, how these four hubs are like let us say doing activities in their particular domains, and what are their mandates. Okay, apart from technology development, as you saw, there is like let's say other activities like startup, international cooperation, HRD, and so on. So now I am coming more into the technical part, and that of quantum materials and devices. So as one of the attendees asked a question about like let's say various materials and technologies that we are developing, so I'm going to tell you about like let's say these material platform devices what we are developing, the national facilities that are coming up under the quantum materials and devices hub. And always remember, whatever right now we will be like let's say discussing or showing you, they are having a particular application in one of these other three hubs. Okay, whatever we material device we develop is going to have an application. It is not just like let's say a material which is of potential use we will be developing. It has to has a application, direct application in one of these three hubs. So coming to, like, let's say the thematic hub at IIT Delhi, which is on quantum materials and devices. So one of the, like, let's say material systems, material platform that we will be developing is what we call 3-5 compound semiconductors. All of you have heard about compound semiconductors, so I will elaborate it little bit also, and then talk about the quantum devices, quantum materials that we are developing based upon these 3-5 compound semiconductors. So the second hub at IIT, second spoke at IIT Bombay, or the technical or technology group is at IIT Bombay, which is working on 2D quantum materials. There are a lot of different types of 2D materials are there, and they are working on these 2D quantum materials for development of certain, like, let's say materials, certain devices. And the third material platform is silicon nitride based integrated quantum photonics at IIT Kharagpur. And what are the activities? I will just, like, let's say highlight those activities, and then if there are more questions we can discuss about those also. So having said that, let me start with a kind of, like, let's say, if some of you are from the semiconductor background, I think it will be a very familiar graph for you. But if you are from some other field, little bit like, let's say, not so familiar, so I will try to, like, let's say, describe it very briefly. You see, in this graph, what we have shown is for semiconductors, on the y-axis, the energy band gap, Eg, which is a characteristic parameter of a semiconductor. Okay, and on the x-axis, their corresponding lattice constant. So most of the semiconductor systems or semiconductor materials, let us say silicon, germanium, gallium arsenide, indium phosphide, gallium nitride, which are having wide, like, let's say, applications in the market today, they have primarily two crystal structures, either, like, let us say, cubic or hexagonal. Okay, what we call is diamond or zinc blende, which is what we have is called, like, let's say, the cubic. And second one is the woodside, which is like gallium nitride or hexagonal lattice. So we are taking their lattice constant. Okay, what is the lattice constant? You can see starting from 5.5 angstrom to 6.5 angstrom, and then the band gap values which have been shown is from very low values of a, like, let's say 0.1 or 0.2 electron volt, going up to, like, let's say, more than 2-3 electron volt. Okay, so all these, like, let's say, dots are showing, representing a particular semiconductor material. Let us say here it is indium phosphide. So indium phosphide is band gap is, like, let's say, 1.35 electron volt, or close to that one, and then this is the lattice constant, close to 5.9 angstrom. So now if you have, like, let's say, gallium phosphide, which is here, and then you also have, like, let's say, indium phosphide, gallium phosphide, aluminum phosphide. So what it shows is that if you want to do, these are three different materials: aluminum phosphide, gallium phosphide, indium phosphide. So one of the element is coming from group 3 element of the periodic table, or group 3 of the periodic table, and another element is coming from group 5 of the periodic table. That's why they are called 3-5 compound semiconductors. They are compound semiconductors. Silicon, germanium are elemental semiconductors. So these semiconductors, they have a particular characteristic value of their band gap. Like, this is indium phosphide, this is gallium phosphide, aluminum phosphide. But with the sophisticated band gap engineering technique, material synthesis technique, we can tune the band gap also now. So how the tuning is achieved? Tuning is achieved through the, like, let's say, alloying, mixing. So what we can do is, there we have techniques, I'm going to talk about that. We can mix gallium phosphide and indium phosphide in any proportion, starting from 0 mole fraction to, let us say, 100%, like, let's say, mixture, or, like, let's say, 0 x is equal to 1 to x is equal to, like, 0. So we can change from indium phosphide to gallium oxide, going from indium phosphide, indium gallium oxide, indium gallium phosphide, and ultimately ending into gallium phosphide. So this is what we call the alloying of the semiconductors, and these semiconductors are called ternary semiconductors, because in that you will be having certain mole fraction of indium, certain mole fraction of gallium, and then the phosphorus. So this is also called, like, let's say, band gap tuning. now we can tune the band gap along this line. You see, this is the line which is being shown. So you can tune the band gap from 1.3 electron volt to, let us say, 2 electron volt. This is what we call the band gap engineering. So similarly, all these lines are showing actually. So let us say this is indium antimonide, this is aluminum antimonide. If we go along this line, I can do the alloying of aluminum antimonide and indium antimonide and tune the band gap from, let us say, 0.3 electron volt to 1.6 electron volt. So this is like, let's say, a big advantage I can get by this kind of mixing. And this is what we do actually in the semiconductor heterostructure development, and this is what we also do in semiconductor quantum heterostructures, quantum devices fabrication. We fabricate, like, let's say, we synthesize new kind of materials which are not existing as such, but we synthesize new based upon, like, let's say, various considerations, and we have sophisticated tools, growth systems by which this can be done very precisely. This is what I am now going to tell. So our technology group 1, which is at IIT Delhi, as you can see, so try to see, like, let's say, the themes and the associated deliverables of each of these technology groups, and what it is doing, like, let us say, where it is feeding, who is taking this technology. So we are developing single photon source and single photon avalanche detectors, particularly at telecom wavelength, okay, close to, like, let's say, 1.5 micrometer, and also high frequency devices which are based upon indium phosphide based epitaxial semiconductor. Epitaxial means, in a sense, single crystalline thin films. Single crystalline thin films we are going to develop based upon phosphide systems and arsenide systems. So this is the whole group. And what are the objectives? As you can see, we have very, like, let's say, specific deliverables. And one of the deliverable, if you see this one, is indium phosphide high electron mobility ultra low noise amplifier. So high electron mobility transistors, they are specific type of transistors which can work at very high frequencies where silicon based, like, let's say, CMOS transistors cannot work. So these can work at communication frequencies like tens and even hundreds of gigahertz also. So this is based upon a quantum heterostructure which we develop, and then there is a two-dimensional electron gas which is a quantum system, and this two-dimensional electron gas is used for transistor fabrication. And in this case, we will be using this indium phosphide high electron mobility transistor for development of ultra low noise amplifier. So these ultra low noise amplifier will be used as a pre-amplifier in the superconducting qubit, because a superconducting qubit, when it sits inside, like, let's say, a dilution refrigerator, so this is at a very, very low temperature, means ultra low temperature in tens of millikelvin, very low temperatures. And then surrounding that, so there will be RF signals, and these RF signals actually, like, let us say, will be amplified by these low noise amplifier, and these will be sitting at 4 Kelvin ambience. So there is a qubit which is sitting at tens of millikelvin. There is a pre-amplifier, HEMT based pre-amplifier, which is sitting at 4 Kelvin. So, and these have to be ultra low noise amplifiers. So in current technologies, these are the best, like, let us say, kind of pre-amplifiers which can work at 4 Kelvin. So that's why this is the technology which we will be developing for, like, let's say, the superconducting qubit technology group. For the computing group, we will be developing this technology. So here what will be involved is the materials involved development. So it's not only the device fabrication, we will be going from material growth. Okay. Material growth will be done, then the device design will be done, the device fabrication will be done, the device packaging will be done, and then this packaged device on a circuit will be provided to the quantum computing hub for their, like, let's say, readout circuit. So this is how it has been structured. You see, it is directly feeding into the quantum computing. Second one is on-demand single photon source at telecom wavelength for all, like, let's say, photonic qubits. For quantum communication, we require single photon sources at telecom wavelength. They travel through, like, let's say, this fiber optics and enable the quantum communication. So once developed, and these single photon sources are based upon the quantum dot. What our group is going to develop, I will show you our team also. It's not that I am expert of these technologies. There are other faculty members who are expert who are developing this one. That's why we require actually a group of faculty distributed across various academic institutions who have the right kind of experience and expertise, and then we join hands, come together and develop technologies, device technologies for the other thematic hubs. Another one important thing is, if you have a single photon detector, then you also need to have single photon avalanche detector at telecom wavelength, and this will also be developed based upon the same material system. Indium phosphide, gallium arsenide material systems we will be developing. So we require material. So material is 3,5 compound semiconductor, and then we have 3 devices, and these 3 devices we will be developing. So as you can see also, like let's say, these are some kind of cross-sectional TM images of semiconductor heterostructure. All these dark and like let's say light regimes which you are seeing, they are the quantum wells grown by technique what we call the molecular beam epitaxy. This is a kind of image of a molecular beam epitaxy. I am going to tell you more about that one. And then these are the HEMT transistors. As when after once you fabricate them, this is the SEM image of this one, and the HEMTs which are going to be used in this kind of circuit. So one of objective of this, like let's say, our technology group is, and IIT Delhi hub is also to develop, to start, like let's say, establish a national facility. This national facility is going to be a kind of like let's say 3-5 semiconductor foundry in the sense that arsenic and phosphide based 3-5 compound semiconductors will be developed, will be grown actually, okay, will be grown by molecular beam epitaxy and then metallo-organic chemical vapor deposition. So these are the 2 techniques which are also like let's say the industry standard. For example, all your LEDs, what you are using, white LEDs, they are developed like let's say the material is grown by metallo-organic chemical vapor deposition. Similarly, the lasers that you are using or the transistors that you are using, they are also like let's say grown using MOCVD, and certain epitaxial layers are also grown using molecular beam epitaxy. These are the best techniques for the growth of very high quality, very high purity semiconductor quantum heterostructures. So this is like let's say the kind of background for the deliverables that we are developing and the materials growth technology that we are like let's say establishing. So if you see, this is like let's say our project team, which is for the technology group 1 at IIT Delhi. You can see that we are starting from material growth and characterization. See, we require materials, very high quality materials, and materials at scale. Okay, we don't want to confine only to 1 by 1 centimeter square. Eventually, we have to develop the technology for a full wafer, 4-inch wafer, 2-inch wafer, and so on, so that like let's say hundreds and hundreds of devices can be fabricated in one particular parallel processing. So we have experts from material growth and characterization. I'm not going to name them, but they are coming across various institutions. You can see we have almost 9 to 10 faculty members from IIT Delhi. IIT Bombay, we have 2 faculty members. So this IIT Bombay team is like let's say expert in fabrication of indium phosphide based high electron mobility transistors. So this is their actually like let's say expertise. IIT Roorkee, Professor Karun Rawat is developing like let's say the circuits which are required, which ultimately will be used in the preamplifier, ultra low noise preamplifier at low temperature. Professor Samit Ray for materials growth and like let's say characterization, and then SSPL and GATEC, which are defense lab, they will be like let's say doing the upscaling of this technology. We will be like let's say developing the technology up to like small scale, and once we have demonstrated the technology, device technology, if you want to take it to the wafer scale, then GATEC at Hyderabad and SSPL in Delhi will be involved in that work. So you can see people having expertise in single photon source, single photon detector, circuits for system development. We have like let's say specific circuits are required for single photon emitters. So those circuit people from electrical engineering department are also here, and materials and device design and simulation. Okay, so you can see like let's say the whole team is centered around this 3-5 quantum materials and devices technology, and various expertise are there, starting from material design, device design, material synthesis, device fabrication, packaging, circuit, and final, like let's say, the development of packaged device. So what I will do is, I'm just like let's say to impress upon you what is the importance actually, like let's say, of these techniques, the growth techniques. So one example is the metallo-organic chemical vapor deposition of single photon detectors. So I think some of you might be working in the area of like let's say for detectors, photo detectors, what we call. So photo detectors like let's say can detect different wavelengths of the electromagnetic spectrums. You have visible wavelength photo detectors, you have IR photo detectors, you have UV photo detectors, even that we also have X-ray photo detectors. So in this case, like let's say, and it depends what is the band gap of a semiconductor. So if the band gap of a semiconductor is higher, it can detect UV photons. If the band gap is smaller, it can detect visible. Much smaller than that one, it can detect IR photons also. These are called IR photo detector. So this single photon detector is also a IR photo detector, but with some, like let's say, special features, which is the avalanche detection. So we know about, like let's say, avalanche multiplication in a PN junction diode, so that we have very weak current, and you can, like let's say, multiply this current by this avalanche multiplication process in a PN junction diode. So this particular effect is being used in this single photon avalanche photo detector, and this is, like let's say, a schematic. It's just a schematic of the layer structure which is there. So you can see there is an indium phosphide substrate. So this has to be procured. And then there are some epitaxial layers which will be grown. These will be grown by MOCVD. And there is a indium gallium arsenide absorption layer. So you can see already there is a ternary semiconductor. There is indium gallium arsenic phosphorus. This is a quaternary semiconductor. Then there is a indium phosphide cap. And then there is a kind of, like let us say, top layer which is P. Okay, so this is a PN junction overall. But this whole, like let's say, structure has been designed by us. Definitely these designs are existing, but we have our own design also. And this is a kind of device. The photons will be incident from the top, and eventually these kind of detector will be able to detect even a single photon also. And this is a typical thickness. A typical thickness of substrate, like let's say, substrate is typically 400 micrometer, buffer layer 1 micrometer, grading layer. So all these things, like let's say, comes under the materials design, okay, and the device design. How the material you are designing, you shall be able to deposit also. It's not that any material you design, sometimes what happens is you cannot deposit it. Okay, so by this MOCVD technique, you shall be able to deposit that also. So a lot of, like let's say, knowledge shall be there within the group, so that you can design an appropriate material and then an appropriate device also, which eventually has to work as a single photon avalanche detector. Now I come to the second example, which is for single photon emitter. Professor Shantanu Manna, he previously worked in, like let's say, Johannes Kepler University in Austria, and developed this technology for growth of single photon detectors. So there was a question about quantum dots. So he is expert in quantum dots, and he grows these quantum dots. These are semiconductor quantum dots actually, because quantum dots can be grown by various methods. But these are actually, like let's say, semiconductor quantum dots, which are grown by molecular beam epitaxy. This will be molecular beam epitaxy. You will be having an ultra high vacuum chamber, and then you will cause a deposition of these kind of quantum dots. So one structure you can see is, like, you take a semi insulating indium phosphide substrate, and you grow, like let's say, indium phosphide epitaxial layer. In between, you embed indium arsenide quantum dots. Okay, you need to know this technology. It's not so straightforward, but the material is indium arsenide here, whose band gap is small. So this can, like let's say, emit at 1550 nanometer, which is telecom C band wavelength. Second thing is also, like let's say, you can have indium arsenide quantum dots, but embedded inside gallium arsenide matrix. Okay, you grow gallium arsenide, in between you embed indium arsenide quantum dots. So this will emit at 13 nanometer. We have a lot of results. His group has produced a lot of results on this one. Can share also the research papers. But this is the, like let's say, the idea about the development of semiconductor quantum dots. And as I told you, these kind of quantum dots can only be grown by either MBE or MOCVD. So in this case, because MBE technique, actually the purity of the material what you are growing is better than that of MOCVD. So in certain cases, it is advantageous to use molecular beam epitaxy. So this is like, let's say, and you can typically see also the indium arsenide quantum dot size is only a few nanometers, 6 nanometer height, and sometimes like, let's say, 10 nanometer height, so that you see the quantum confinement. You need to see the quantum confinement in a quantum dot, so that, like, let's say, you can cause the emission of a single photon from there. And this is like, let's say, another this thing, which is the MB of hemp structure. Okay, hemp, again, it is a quantum heterostructure. Okay, I think maybe some of you might not be getting exactly what I'm trying to explain, but what, like, let's say, I can tell you that using this MBE, you can grow various layers. Okay, you can see all these semiconductor systems. These are, in a sense, artificially created semiconductor materials, and with very precise control. For example, you see indium 0.52, aluminum 0.48. It means the mole fraction of indium is 0.52, aluminum is 0.48, and then it is arsenic. So it is called ternary indium aluminum arsenide. Why you grow only this composition? Because it is lattice matched to indium phosphide. If you don't grow a lattice matched material, then there will be a lot of dislocations which will happen during the growth, and these dislocations will kill the performance of the device. So that's why you have to be very careful about the growth of the material, which material you are going to grow on which substrate, and you have to minimize the defects also. If you have a lot of defects, then the device is not going to work. So it had all these things have been very carefully engineered. And one thing is the design, and second thing is, like, we shall be able to deposit also. This is also another thing. You shall have the right kind of expertise to deposit, let us say, this much with 500 nanometer, or indium aluminum arsenide spacer with 3 nanometer, so precise, 8 nanometer. And here there will be a two-dimensional electron gas formed due to the quantum heterostructure. There is a wide band gap semiconductor, low band gap semiconductor. At the interface, there will be a two-dimensional electron gas, which is used for the fabrication of high electron mobility transistor. So I have, like, let's say, enumerated already, like, some of the properties of the MB, like molecular beam epitaxy provides the necessary control. It provides you, like, let's say, control to the atomic level. Okay, you can control one atomic layer actually. That is the kind of precision you can achieve by molecular beam epitaxy, and this is highly required for the materials which are for quantum technology applications. So now I come to, like, let's say, at IIT Delhi, we have one MBE system for the growth of selenium and tellurium based 2D quantum materials and heterostructures. So as I was telling you in my first lecture about the Sonipat campus, so at Sonipat campus, we have this MBE system, and you can see, like, let's say, at the outset, if you see, it seems to be, like, let's say, a kind of complex system where a lot of chambers are there, number of cables, pumps, electronic systems, and all those things are there. So this is from a French company, Vinci Technology, and it was established of 3-4 years back by my 2 PhD students and 1 postdoc. So they established the whole system from the scratch. So this is, like, let us say, a chamber, ultra high vacuum chamber. Ultra high vacuum chamber, this chamber can go to less than 10 to the power minus 10 millibar. Okay, just think about the vacuum level. 10 to the power minus 10 millibar level it can go to. Okay, and then it is connected to other chambers. Okay, these are the pumps, these are the vacuum pumps. So there are vacuum pumps attached to it, like cryo pump, ion pump is there, titanium sublimation pump, which can take the vacuum down to 10 to the power minus 10. And then there are buffer chambers and the storage chamber. So when you introduce the indium phosphide substrate or sapphire substrate onto which you want to deposit this semiconductor quantum heterostructure, you have to transfer it from, like, let's say, the high vacuum to the ultra high vacuum. And this is the chamber where they are deposited, and these are the K cells actually. So for MBE, MBE is a physical vapor deposition technique. So that's why it is called MBE. Okay, and when it is deposited, what happens is, actually, this is the material is embedded inside this one. Okay, material is embedded inside this K cell, and when you heat it, it will evaporate. So it is a kind of physical vapor deposition. It will go in the form of a molecular beam. Okay, something like, let us say, light coming out of a torch. So that's why it is called molecular beam epitaxy, and inside it, this is the viewport from where you can see how the growth is happening. So it's a, like, let's say, one of the first MB systems in India on selenium and tellurium based 2D quantum materials. And if you see here, what are the various sources we have available? So in an MB system, it depends, as I was showing you in the first graph, energy band gap versus the lattice constant. What are the various materials you can deposit, and how you can engineer the growth of the material and tune the band gap? So we have, like, let's say, available tungsten, molybdenum, and platinum. And then we have all these elements available in the K cells. So you can see selenium is there, tellurium, indium, gallium, bismuth, antimony, cobalt, and manganese. So if you have certain background in 2D quantum materials, you may remember that molybdenum diselenide, MoSe2 or MoT2 or WSe2 or WTE2, these are very popular 2D quantum materials nowadays, and they are grown by various methods, starting from solution growth to a very crude kind of chemical vapor deposition to hydrothermal and so on. But the advantage with the MB is that you can get highly pure, and the control is one monolayer, as I have told you. So the one atomic layer, like, let's say, you can grow one atomic layer of WT2, then another atomic layer of WSE2. These kind of control is there with this MB, and you can use lot of permutation and combination. If you want to deposit indium telluride, that also can be done. If gallium selenide is required, that can also be done. You can deposit topological insulators like bismuth diselenide or bismuth tritelluride, Bi2T3, Bi2Se3. These kind of compound materials, which are topological insulators, can also be deposited, and then the metals can also be deposited. So this is, like, let's say, the K cell, what I was talking about. This is the E-beam evaporator. This is the effusion cell, K cell or the effusion cell. This is the material. Suppose in this you have selenium or indium or gallium, and then it is heated. So this is the crucible. Okay, this is the crucible, and then you can see, like, let's say, how it is loaded. Okay, there are heaters and so on, and then it goes inside the MB chamber. So now I come to, like, let's say, the metallo-organic chemical vapor deposition, because this is the another very important, like, let's say, technique which is used, but it is different from the MBE. It is, as the name indicates, metal organic chemical vapor deposition. So MBE is a physical vapor deposition, and this is a chemical vapor deposition. So there are some reactions which are happening in the, like, let's say, or precursors which are in the chemical phase, and then when they come in touch with the substrate, then a chemical reaction happens which causes the formation of a semiconductor layer. So you can see this is the reactor. So actually this technique also involves metallo-organic, which are in certain cases toxic also, and there are some toxic gases used. So you have to be very, very careful. So there has to be a gas handling system, complete gas handling system, which can handle all these kind of toxic chemicals. Okay, so metallo-organic means trimethyl gallium, trimethyl aluminum. So these are the metallo-organics which are used. So epitaxial layers of gallium arsenide, gallium nitride, indium phosphide, zinc oxide, gallium oxide for 2-DEG high electron mobility, LEDs, laser diodes, photodetectors, quantum wells, super lattices, all these kind of, like, let's say, heterostructures, this is used. Okay. One important thing you see here is this is the chamber, this is the gas cabinet. So where from the gases are coming. This is the load lock, electrical panel, computer software system is there. And this is how, like, let's say, the wafers will be loaded. It is an industry scale actually system, what I'm showing you here. So many wafers. So in one go, you can deposit maybe on 24 wafers or 10 wafers. Okay, this can be easily done with the MOCVD. So if you want to scale up the production of a particular material, so semiconductor material, then MOCVD is actually the technique. That's why the LEDs what you are getting, they are deposited using metallo-organic chemical vapor deposition, and the vacuum typically here is in this range. Okay, it is not ultra high vacuum, 0.5 to 760 torr. Okay, so the applications, so the So the applications of MBE and MOCVD. So apart from the quantum devices, so you see, I have given you example of two quantum devices, single photon emitter and single photon avalanche detector, but they can also be used for other kind of quantum devices like photonic integrated circuit devices, two-dimensional electron for studying quantum Hall effect, and quantum cascade lasers, heterojunction bipolar transistors, terahertz electronics and optoelectronic devices, okay, for defense and medical application. So once you have this growth system with you, what you require is the growth system. Then you can grow epitaxial layers for various kinds of quantum heterostructures, semiconductor quantum heterostructures, which can have applications beyond even quantum devices also. That is actually the advantage of molecular beam epitaxy and MOCVD. So now I come to the very briefly. So you see, I have in nutshell told you the activity, and what I want to tell you is that IIT Delhi will be establishing a national facility, one MBE and one MOCVD for 3-5 compound semiconductors. So it may take some time, but once it is established, it will be available for all the quantum users, National Quantum Mission users, and they can send their design that this is the epitaxial layer they want, and then it can be deposited here. So they don't need to have their own system because it is very, very costly. It's a $2 million kind of growth system. So everybody cannot keep in their own place, but this will be provided at one particular location at IIT Delhi, and it will be available for all the users. So the second one is, which is the technology group on wafer scale emitter and detector arrays for visible wavelength room temperature photonic quantum technologies. Here the lead BI is Professor Saurabh Lodha from IIT Bombay. As you can see, there are many members in their team, and what they are actually, like, let's say, developing for the other three verticals. So their aim is very specific. They want to develop visible wavelength single photon emitter and avalanche photodetectors. You see, our group is working on the material platform, which is 3-5 compound semiconductors. We are making single photon emitter and detector at telecom wavelength. So their material platform is 2D quantum material, and their device is single photon emitter and avalanche, but at, like, let's say, visible wavelength. Okay, so ours is telecom wavelength, theirs is at visible wavelength. So they will be developing the whole technology. So it's not like, let's say, so straightforward one. See, we have to start, or their group has to start from the 2D quantum material growth and modeling. So first thing is on large scale. That itself becomes a very big challenge, 2-inch wafer. Okay, and then the characterization. Characterization at a higher scale, 2D material at 2-inch wafer if you want to grow, and then you want to characterize for its uniformity of the growth, it becomes itself a challenge. And then finally the device fabrication and the integrated chip fabrication. Okay, so this is, like, let's say, they will be developing 50 cross 50 array and integrating it monolithically with a silicon CMOS ASIC actually. Okay, so that this is provided as a complete, like, let's say, a device package to, let us say, quantum communication hub, so that they can use it for their application. So as you can see, what I want to tell you, because some of you were asking that how they can also provide, like, let's say, apply for projects in the future. So you see, this project team is quite big. So there are faculty members across various institutions who are specialized on 2D materials growth. Okay, wafer scale growth by MOCVD and then by MB. So these two, like, let's say, faculty are doing by MOCVD and they are doing by MB. Then also material characterization and transport modeling. Okay, you have separate set of faculty for theoretical calculations and modeling, and then the device fabrication as well as measurement. So single photon emitter and for single photon detectors, we have the expert faculty. They will be fabricating, the material will be grown by these, and then the fabrication of devices will be done by these faculty members, and also the measurement. Okay, and then the system integration, on chip integration and testing will be done by these two faculty from IIT Bombay in the electrical engineering departments. So what they are in deliverable is 2D single photon emitter and single photon avalanche detectors for quantum technology, for quantum communication applications. So now the final technology group, which, like, let's say, I want to introduce is our IIT Kharagpur group, which is working on a very specific technology, which is reconfigurable and scalable photonic qubit architecture. Okay, and for quantum computing applications. So they have expertise in heterogeneous and monolithic, like let's say, integration. And if you see, the objective, like let's say, starts from design and development of various individual building blocks of quantum photonic circuit. So in quantum photonic circuits, there are various kinds of materials and device, like let's say, components are required. You require the development of thin films of silicon nitride, very high quality, and you also require actually single photon emitters and detectors which are integrated within the same chip. So this what we call the quantum photonic circuits. Then the design, fabrication and characterization of quantum sources, 2D material coated, tapered fiber based, and also micro ring resonator based quantum frequency foam. So this is a very important component. This is one component which will be eventually used by quantum communication or quantum computing. Creation of squeeze states, so their expert group is expert on this one, and also the control and readout electronics for photonic qubits. So these are, like let's say, the project deliverables. Everything has a particular timeline. The material system is silicon nitride, and various processes and technologies will be developed by their group. So now coming finally to the future directions. Future directions, right now our groups have just started. In the last 1 year we have started doing some technology development, so we are working on design. So these three technology groups, now you clearly know what are the material systems and what are the device, like let's say, devices we are fabricating. So design, development and packaging of single photon sources, single photon avalanche detectors, high electron mobility transistors and photonic qubits. So this is, like let's say, the our future goal. And setting up of advanced growth techniques, I have given you example of national facility on MB and MOCVD for high quality materials, high purity, high quality materials. But in future we are also exploring possibilities, and there are proposals already in the pipeline on new kind of materials such as spintronics, topological insulators. They might not be on the high priority right now because they are more blue sky kind of research, but definitely there is a, like let's say, in coming time, if there are proposals which definitely show that these materials and devices can be used for some application in computing or communication or sensing, they can definitely, like let's say, be considered. And high TC superconductors. So tomorrow my lectures are on superconductivity. So we have, like let's say, a big group at Tata Institute and in Bombay on superconducting qubit development, and that's why the superconductivity is a very very important theme in this whole, like let us say, quantum mission. And then the oxides and heterostructures are also important, and another important thing is national international collaborations and partnerships, and engagements and cooperation with industry and startups, which I have already, like let's say, told you briefly about. So these are, like let us say, the future directions for our quantum QMD hub. And I think with that I will, like let's say, thanks all the attendees who are very carefully, like let's say, listening to the lecture, and then we can again open up the session for Q&A. So thanks.
Thank you, Professor Rajendra Singh, for very nice and very informative lecture. Ankita, I hope you can hear me clearly.
Yes, sir. I can hear you clearly.
Okay, that's good. So Professor Rajan Singh has covered all about like what the facilities under this NQM mission are being developed at IIT Delhi, mainly about the molecular beam epitaxy and MOCVD. These are very high-end analytical tools for the deposition of single electron emitters. And obviously they are very costly, so it's not possible to have those facilities at every institution. So it's good that under National Quantum Mission, these facilities are being developed at IIT Delhi. So those who are working under this project, they can directly use those facilities. And then Professor Singh has also mentioned about what at IIT Bombay, Professor Lodha group is working for single photon emitters, mainly in the visible region, visible wavelength region. And then he has also briefly described about the facilities related to this mission at IIT Kharagpur, what those people are doing about the qubit architecture and other things. And then finally, he has also mentioned about other small areas like spintronics, superconducting qubits development, and other things which are presently not in focus or not in the priority, but maybe in future under NQM, Professor Singh will also be looking at those proposals on these low priorities areas. So thank you, Professor Singh, on behalf of EICT Academy Jaipur, as well as on behalf of other academies of EICT across the country, because it's a joint project program where we have the participants from EICT Academy, IIT Kanpur, IIT Roorkee, NIT Patna, IIIT Jabalpur, and from other EICTs. So on behalf of the coordinators of all those academies and on my personal behalf, I extend my heartfelt thanks to you for being with us, for delivering today the lectures, mainly about the National Quantum Mission and the QMD Foundation of IIT Delhi. So now the session is open for question answers. Ankita, can you take few questions quickly?
Yes, sir. First, I would like to thank you, sir, for this wonderful lecture. And we take few questions which are related to this lecture. Sir, the first question is, how does single photons produce from the quantum dots? By Dr. Chandrasekhar.
Okay, so I think for that we need a kind of like, let's say, more elaborated, like, let's say, kind of presentation. So you see the quantum dots, there are various ways of, like, let's say, single photon emission. So first thing is to confine, like, let's say, the electrons. So how the photons are emitted, so you have a quantum well, okay, or like it's a three-dimensional quantum well. So from the conduction band states to the valence band states, when the electron, like, let's say, makes a transition, there is a photon which comes out, like, let's say. Now there are two ways, as I told you. One is the electrical pumping and another one is the photon pumping. So you shine a photon having higher wavelength or like a higher energy than the band gap of the semiconductor, plus, like, let's say, whatever extra energy comes from the quantum confinement. The energy shall be more than that one. And when it goes back to the ground state, there is an emission. But now, like, let's say, we have to induce certain kind of, like, let's say, ways by which it shall not be, like, let's say, multiple photons coming out of it. So one way of the ways is electrical pumping, like, let's say, you give a pulse actually, so by a pulse, and then what you get back is a single photon with a very precise energy, because the energy levels in the quantum dot are very precise. Okay, so this is the way by which you can cause, like, let's say, the single photon emission. And then there are also ways how to detect, because you see whether I have got a single photon uh, emitted or not, so I shall be able to detect that also. So this Professor Shantanu Manna, as I told you, he has the expertise in this area, and maybe I think connected with this one, I would like to apprise the whole people, like, let's say, audience, that at IIT Delhi we are also developing two characterization system. One characterization system is to detect single photon emission. Okay, there are, like, let's say, photo detection systems which can detect whether a photo detector is working or not. But here we will be developing a system which will measure the single photons. Okay, it is called single photon emitter characterization system. Similarly, we will also be developing single photon avalanche detector characterization system. Characterization of the detector, characterization of the emitter itself, and this again will be also a kind of national facility. And once it is developed, it is, like, let's say, right now under development. Another 6-8 months we will be developing it, and then it can also be used by the quantum community. So if you have developed, let us say, a source and you feel that it is a single photon source, but how do you tell, how do you characterize? So for characterization you can come to IIT Delhi and measure that it is really a single photon.
Thank you, sir, for nicely explaining the question. The second question is, coming from a classical engineering background, where we work with visible bulk materials that we quantify by weight and evaluate for long-term structural fatigue, quantum materials seem like a completely different paradigm. To help bridge this gap for those of us from other domains, can we actually see these materials with the naked eyes once they are integrated into a device, or we strictly dealing with atomic scale structures?
Okay, so I think it's a good question in a sense that it is coming from a person having different expertise. So you see, when we develop these single photon emitters or single photon avalanche detectors, there are ways to see them also, okay, even in direct space. Okay, so there are techniques, very sophisticated techniques like transmission electron microscopy or scanning electron microscopy or scanning tunneling microscopy, by which we can also see the material. Okay, we can see also, like let's say I have not brought it today because right now we have not grown, this is grown somewhere else, our own samples are not there, but there is a plenty of literature available. See that a single quantum dot or multiple of quantum dots, how they are arranged, what is their shape, everything can be, like let's say, quantified and characterized also in real space. So in a sense you can see them also.
Okay, sir. And after he also asked, furthermore, since we cannot quantify them by the bulk weight, how do we practically measure and standardize them during manufacturing? And what is the typical operational lifespan of these quantum states before material degradation sets in?
Yeah, so you see, like let's say all these semiconductor devices, definitely they have their lifetime. LEDs, as you know, they are also, like let's say in LEDs also there are quantum wells. Okay, the light emission in an LED comes from a quantum well, and all of us know LEDs have a certain lifetime. Each device, each material has a certain lifetime, and typically LEDs have a lifetime of 10,000 hours. And these quantum devices, right now I don't have the numbers, but definitely it shall be a few thousands of hours, because ultimately it has to be used in a quantum network, and in a quantum network it has to work continuously for years. So it shall have a lifespan of at least, let us say, a few years to start with.
Okay,
But
thank you.
ultimately it will also fail at some point, and then you have to replace it, like LEDs we replace now. So you have to replace single photon emitters and detectors also after number of years.
Okay, thank you, sir. Sir, the another question is, what is the criteria for selection? First, setting up quantum lab, and second, proposal under quantum algorithm.
Yeah,
They
so
already
the
applied.
yeah, so proposal under quantum algorithm, as I told you, you have to contact actually the quantum computing hub at IC Bangalore to know the status. Second thing is, what is the criteria? So as I have been telling you, whenever there is a call for quantum teaching lab, so there are certain criteria you have to fulfill. So those criteria you can either get from us also. So one of the criteria I can tell you is that you shall have a running quantum technology program in your institution, either a minor degree or a full-fledged MTech or BTech program. That is a criteria. Second thing is, your institution shall provide at least 2000 square feet of space for the establishment of this quantum teaching lab. Third thing is that you shall have enough number of faculty who can teach also these courses. Okay, so there shall be some inherent, like let's say, strength within the institution to take forward these quantum technology courses. Okay, so these are certain criterias, and then you shall be open to share 50% of your time of the quantum teaching lab with the surrounding engineering as or other institution. So this, since it is funded by the quantum mission or the DST, so there is a criteria that your institute shall agree that 50%, I think somewhere around 50%, you shall use for yourself, 50% you shall allow other, like let's say, surrounding institutions also to use it. And then the Senate approvals and all those things shall.
Okay, thank you, sir. Sir, another question is, does the fabrication facilities is started, or it will take more time? And what is the process to get access of IIT Delhi fabrication facilities? Sir, your voice is not coming.
No, sir, still it is not coming. I think again there is some network issue. Though it was the last question, I think it seems there are no further questions. So, sir, still your voice is not coming. Yes, I'm getting. Yes, sir, voice नहीं आ रहा है. Okay.
Maybe you can so that the other people can do it.
Yes, sir. Yes, sir. I'm doing that.
Yeah. So you see, the usage of, like, let's say, NRF facility, fabrication facility is another channel. You can use it. It's already available on the net. Then you can become a kind of registered user, and there are certain charges, and then you can start using the free facilities at IT. If still there is doubt, you just write to me, and I will link you to the, or connect you to the right person at IT.
Yes, sir. Thank you. Thank you, sir. I will just disconnect the call and I'll come back to the screen. So thank you, participant. It seems there is no further question. I express my gratitude again to Professor Rajan Singh. And it was a wonderful section in the sense that all the participants, they could get the chance to interact with Professor Rajan Singh and to ask the questions. Because Professor Rajan Singh is so busy being the director of the QT Foundation, one of the T-Hub at IIT Delhi. It's not so easy for him to have one-to-one interaction with each and every participants. But through this FDP, he is able to at least give some time to us. Thank you, sir. Thank you for joining with us. And as a part of our policy in the ICT Academy, we are sharing the PDF files of our lectures with our participants, as well as the recorded videos, because these lectures on online platform are being recorded. And then we will be sharing the link on our hard drive, Google Drive, link for this recorded video, so that those who could not join online, they can, in the late hours, in the late evening hours, they can go through those lectures. So if possible, if whatever the content, if you would like to share with our participants, you may please send us the PDF file. You will be getting soon an email from us, from the EICT Academy, on which you can share those PDF files of the PPTs, which you would like to share with our participants. So with this, now we have come to the end of this session for today. Tomorrow again, Professor Singh would be talking mainly about the superconductors, superconductivity and other related effects. So thank you all the participants. Thank you Ankita and Anuragha for joining, for helping us in this online platform. We may now close this session. All the participants may now please log out.
Okay, thank you. Thank you, sir.